In the real world, the photon never moves like a point object with a definite position at any given time instance. Instead, it moves like a wave without a definite position at any given time governed by quantum laws. The light clocks and rulers used in the classical thought experiments of relativity treat a photon with a definite position at any given time. However, those experiments would never work in reality. They only exist in our imaginations. Those thought experiments get the right answers but with the wrong reason. They are classical calculations, merely pretty, purely hypothetical, mathematical exercises. They should not be used to derive time dilation and length contraction. Instead, the Lorentz transformation shall be used here. Whenever we change the state of a clock from stationary to a steady motion, it appears to slow down in ticking rate. If we jump to the frame moving together with the clock, it restores the original ticking rate. This is called time dilation. Time dilation can be derived mathematically from the Lorentz transformation. For a clock stationary in the second frame x', y', z', and t', let the elapsed time be delta t'. Since it is stationary in it, we have delta x' equals 0. From the inverse Lorentz transformation, we have delta t equals gamma times delta t' plus v divided by c squared times delta x'. That equals gamma times delta t'. Since the Lorentz factor gamma is greater than 1 when the speed v is not 0, we have delta t is greater than delta t'. Whenever we change the state of a ruler from stationary to a steady motion, it appears to be shortened along the moving direction. If we jump to the frame moving together with the ruler, it restores the original length. This is called length contraction. Length contraction can also be derived mathematically from the Lorentz transformation. For a ruler stationary in the second frame x', y', z', and t', let its length along the x' axis is delta x'. Since we measure its length at the same time in the first frame, x, y, z, t, we have delta t equals 0. From the Lorentz transformation, we have delta x' equals gamma times delta x minus v times delta t, that equals gamma times delta x. That leads to delta x equals delta x' divided by gamma. Since the Lorentz factor gamma is greater than 1 when the speed v is not 0, we have delta x is less than delta x'. It is hypothesized by the author that at the most fundamental level of nature, everything in the universe is made of particle waves and field waves. All of those waves, either free or in interactions with others, are governed by the same universal wave propagation operator. The summation with respect to mu from 0 to 3 and the summation with respect to nu from 0 to 3 g mu nu partial nu. In particular, when there is no gravity, the operator falls back to its standard form. -1 divided by c squared time partial t square plus partial x square plus partial y square plus partial z square. Its invariance in form under the Lorentz transformation is the true essence of special relativity. It doesn't matter whether or not the speed of light is constant. This standard wave propagation operator has many manifestations. The examples are time dilation, length contraction, loss of simultaneity, E equals mc square, and most importantly the invariance of the laws of physics with respect to the motion of observers. If we use a computer program to simulate any clock or ruler using the universal wave propagation operator at the lowest level, we always get time dilation, length contraction, and any other relativistic effects. This is the true cause of all relativistic effects. It simply doesn't matter whether or not the speed of light is constant to have those effects.